Modern computer chips are hitting a physical wall. As we pack more processing power into our phones and servers, the devices are generating temperatures that are becoming impossible to cool. The root of this heat problem comes down to how data is processed. Traditional chips work by physically shuttling electrons through microscopic wires. Pushing those physical particles around inherently generates friction, and as a result, heat. To eliminate that heat, researchers are testing a different approach. Instead of moving the electron itself, they leave the particle entirely in place and only transmit its vibration, its magnetic spin, passing ripples of energy from one stationary particle to the next. Bypassing the physical movement of charge entirely removes the primary source of friction. This transition from electrical currents to magnetic waves offers a path to run demanding AI models without melting the hardware. To control these magnetic vibrations, which physicists call spin waves or magnons, researchers first have to build a highly specialized medium known as a synthetic antiferromagnet, or SAF. This diagram shows the SAF material structure: two magnetic layers divided by a 0.6 nanometer spacer, a fraction of a DNA strand's width. This tight spacing creates a battleground for two distinct spin waves: a rapid out-of-phase optic wave on top and a slower in-phase acoustic wave below. Trapping these two distinct frequencies within a single medium gives researchers the structural foundation they need. By interacting with these waves, they can manipulate information purely through magnetic vibrations, relying on zero electrical charge. Once the structure is built, the next step is to find its breaking point. Researchers saturated the SAF system with radio frequency power to see what happens when the predictable linear rules of physics fail. Under intense radio frequency drive, the system undergoes three magnon interaction. The stable propagating waves split apart or merge, creating chaos that stops forward travel. They convert into Kittel magnons, stationary waves that pool in place and vibrate without moving across the material. As these stationary Kittel waves overpopulate the material, they reconfigure the environment inside the magnet. The sharp energetic boundaries that normally keep the high-frequency and low-frequency waves separated begin to dissolve. By intentionally overpowering the system to trigger these unstable dynamics, the research team primed the material for a transition that existing magnetic models could not predict. Flooding the system with stationary waves led directly to an anomaly the team could observe. As they increased the external magnetic field, they hit a highly specific threshold. And at that exact point, the high-frequency optic wave abruptly collapsed, transforming entirely into the low-frequency acoustic wave. This line graph plotting frequency against magnetic field strength shows the scale of the transition. The frequency tracks steadily along the top and then instantaneously drops by 5 gigahertz, a jump orders of magnitude larger than previous observations in hybrid magnetic systems. It behaves exactly like switching a radio station to a completely different frequency, but it is accomplished entirely by adjusting a magnetic field strength, requiring zero complex circuitry. This incredible mode-hopping phenomenon proves that we can trigger a high to low frequency shift using only magnetic vibrations. It offers a way to switch signal states instantly, bypassing the need for heat-generating electronic transistors. This mode hopping also possesses a final critical property. The frequency jump exhibits a memory effect that depends entirely on the direction the magnetic field is changing. This continuous loop graph visualizes hysteresis. When magnetic power increases, frequency drops at a specific point on the right. But when decreased, it delays and jumps back up at a different point on the left, leaving a wide gap between thresholds. Because the jump points are not identical, that gap allows the system to hold its current state even as the environment changes. This built-in memory makes the material capable of storing data, acting as non-volatile ones and zeros. Harnessing this magnetic memory mechanism provides a direct blueprint for building ultra-low power computer chips. Specifically, it opens the door to neuromorphic processors, hardware designed to process information and retain memory simultaneously, mimicking the human brain without the risk of overheating. By achieving 5 gigahertz frequency jumps and physical memory within mere vibrations, researchers have moved beyond optimizing old, heat-heavy circuits. They have drawn up the plans for an entirely new architecture of computing.